Well, good morning, everyone, and welcome to today's sponsored webinar, Reducing Your Cost Per Part. Before we begin, I have a couple of short housekeeping items. Today's webinar will be recorded and made available to today's attendees. You will receive an email with a link to the recording in a few days. Second, our presenter, Jonathan Edwards, will be answering questions at the end of the session. To ask a question, click on the Q&A on the menu at the top of your screen. A window will pop up for you to type in your questions. You can type in a question at any time during the webinar. Thank you all for joining us today. Now let me introduce our speaker, Jonathan Edwards. Jonathan has nearly 20 years of experience at Wheelabrator Group as part of Norken. He's worked in a variety of essential roles within the organization, including areas in mechanical engineering design and R&D. He brings a wealth of knowledge to customers as a thought leader in productivity, equipment optimization, and preventative maintenance. He has also previously worked as the Customer Application Laboratory Manager. Currently, Jonathan is Field Market Developer for the Wheelabrator Group. Now I'll pass it on to you, Jonathan.
Thank you, Shannon. Good afternoon to everybody. Today we're going to start out and we're going to do the webinar on how you can reduce your cost per part in the finishing room. Kind of with that in mind, the way that I've kind of structured this is, we're going to talk a little bit about what are the costs, where are these costs coming from, when are the excessive costs occurring. We all know it's a shot blast machine. There is cost incurred with running it. And then which operations contribute to most of my cost, where are these costs occurring, or why are these costs occurring, and how can these costs be reduced? That's kind of the format and how I've broken up most of the things today. Going kind of off of that, on the costs, I've broken them down into two sectors. I have labor and consumables. Under the labor, it's the obvious things. It's the operator to run the machine, and then maintenance, keeping the machine up and running. There on consumables, I've broken it down into abrasive consumption, which we'll really get into and talk a lot about today. It's going to be probably the highest cost for operating a shot blast machine. And then we'll talk about abrasive waste and then the wear parts that go along with maintaining your machine. Real quick, kind of a recap. Everybody out there that has seen a shot blast machine is aware of all of these components that go into them. They all have a blast machine, a material handling section, the blast cabinet, abrasive reclaim. There are different variables of that, and we'll talk about lightly. You got your elevator, your separators, and then a dust collector system. If you're running all of these systems properly, it's going to help you, as I've documented there, increase your production, maximize your operating efficiencies. It will improve your productivity. One of the biggest ones right here, minimize that machine downtime, and then reduce the maintenance times cost associated with any downtimes. All right, going off of that, we're going to start out and we're going to talk about the labor side of it. Labor, these are just incurred costs. They're always going to be there. But you can minimize them just a little bit. Where are they occurring? Operator costs, they vary drastically and rise rapidly if the blast cleaning system is not kept in optimal condition. We all know that's going to be hard on a shot blast machine because the machine basically, I don't want to say is designed, but it functions. It's a pretty violent action inside of a blast machine, and they typically, they eat themselves up from the inside out. So keeping your system going, up and running is key. Some of the things that you can do, routine inspections, evaluations, record keeping. These things are all required to prevent the unnecessary and unexpected breakdowns. It's not going to prevent them 100% by any means, but it's going to hopefully reduce those so that you can schedule your preventive maintenance in a timely manner. As we all know, costly repairs, they can be avoided or postponed if you have conscious operators and a maintenance staff that's watching over the equipment. It's not always the easiest thing to do in this industry to get people to buy in. This isn't always the machine that everybody wants to run. But if you can have operators and a maintenance staff that will take ownership and take into that system, it's going to help you out tremendously. Where are the costs coming from? When it comes to labor, it's a combination of the utilities and power to run it, the air, the abrasive, parts, tools, There we go. Materials and maintenance, labor, and then the operator costs. If you wanted to figure out exactly how much that machine is costing you to run, there's a simple formula for it right there. As the operator of the machine, you should know your operating cost. What does it cost for your labor rates and things like that? Maybe your power consumption. You add that with your maintenance costs. Divide it by the actual wheel hours of blasting time. That's key. On a lot of these machines, they are documented. Well, the machine was out here running for 20 hours a day, but you were actually only throwing shot for 15 hours a day. That's the time that you want to track, the amount of time that it is actually throwing shot. Like I said, you divide that time out, and it's going to give you the cost per wheel hour that it's costing you to run that machine. So when are the excessive labor costs occurring? Like we talked about, there's always going to be some form of labor costs, but the excessive, that occurs a lot when you're planned downtime versus unplanned downtime. If you can schedule that PM out there, it's not going to cost you as much. Whereas if that machine breaks at an unexpected time, it is going to cost you more because you're going to lose production. It may be on a third shift. It's going to require you to get more personnel in there, things like that. So having that preventive maintenance is going to help tremendously. The three key things to remember to try to minimize this: observation, watching that machine, having that operator really paying attention to it. He's going to be your first line of defense. He's going to know when a wheel doesn't sound correctly, when something doesn't look right. He used to clean these parts in a 5-minute cycle time. Now he's having to crank it up to 6 or 7 minutes. That is the machine telling you that something is going awry on it, and you need to start looking at that. And then you make your adjustments accordingly to keep it back into spec, and then controlling it. Like I said, documenting everything that you're doing on it, the operating hours and stuff like that. Those are all key. Okay, so why are some of these excess costs occurring again? Okay, one of it is lack of process controls. The operator, say maybe he's not getting feedback from the finishing room where they're actually looking at the parts and inspector or something, and they could tell him, say, hey, you're actually overblasting these parts. If he is, he could reduce his time. He could reduce, his velocity. That feedback is key to the operator to know. Same with the maintenance department. If we're not telling the maintenance department that, hey, that machine's making a real loud noise that it wasn't making for the last 2 weeks, that's probably an indicator. Maybe they want to go look at a bearing or something like that. So having that feedback is going to be key. And then, one of the highest ones out there, production demands. Got to get the parts out. I don't care if that machine's breaking down. I don't care what's happening. Run it, run it, run it, run it. That's one we hear all the time. Problem with that is it's going to pay me now, pay me later. Sooner or later, you're going to push it too hard, and then you're going to have those unplanned downtimes that are going to cost you probably more money in the long run. How can you reduce any of these? One of the easiest things to do is just to make a preventive maintenance checklist. As you can see on the screen, I just took a little snapshot of some, and I broke them down daily, weekly, and monthly. Things that the operator should do on a daily occurrence, on a weekly occurrence, on a monthly occurrence. That's going to help you tremendously just to have that checklist out there for the guys to do. Another way that you can reduce some of these labor costs is through process controls. A lot of these machines out there, they're old push button machines. There's a lot of new integrations that can be tied into shot blast machines. This is probably one of the areas that the most improvements can be made on them going forward. You can upgrade, with HMIs, PLCs, stuff like that. There are infinite amount of things that can be tracked on these machines. You can put, sensors all over it that can tell you vibration sensors of wheels. Obviously, if your elevators, your screws, if they're tripping out, if they're getting overloaded, you want that machine to shut down. If you got a really highly processed part that you're trying to clean, you can actually set your system up to where if you drop below a certain level of amps being thrown, it will shut down your process. Because if you're not throwing BBs against the part, you're not going to get a good coverage part that's going to pass the next stage. So you could have it, programmed in to shut your machine down there. Those are, like I said, huge things that can be looked at to improve your process and reduce those labor costs. Another key one is service inspections. Having them done monthly, quarterly, biannual, annual, whatever it may be. In the shot blast industry, as we're traveling around, we're seeing one of the ways customers, they're, they're not always, they've had to cut back on maintenance personnel. That's one of the areas that have been cut lately. And then they're hiring people up. The person may not know the most about the shot blast machine. So partnering with the provider of your shot blast equipment to have them come in to take a look at it, to help train the people on what to look for, some of the little intricacies that go along with them. That's going to help you reduce these costs drastically. Next, we're going to talk about the consumables. Like I said, the labor, there really wasn't going to be that much into it. It's the cost that everybody kind of expects, but there are some things to reduce it. Consumables are the main things that go into it. And here I'm going to talk about abrasive consumption, the abrasive waste, and wear parts. Abrasive consumption. Anybody who is running and operating a shot blast machine understands that this is actually one of the highest costs in operating a shot blast machine. Whenever we talk to potential new customers and everything like that, when they are starting to ask, how much is that machine going to cost? What is it going to take me to operate it? It is surprising when you start running the numbers and everything, that abrasive consumption is going to be one of the highest month-over-month things that goes into running that system. Thing to keep in mind, there's always a certain amount of consumption that's going to occur with abrasive. I mean, we're throwing the BBs around, they're hitting things, they're naturally going to wear themselves down and break apart. So it's never going to go away completely, but there are some things that we can do to help you increase that abrasive consumption. And those are the things that we're really going to try to dive into today. Here we go. So when is some of the excessive abrasive consumption occurring? I've broken it down into about 4 different areas with this abrasive consumption. The first one we'll talk about is the impact energy. Okay, so if the impact energy, as the slide says, exceeds the shot material capability. If you can look at the slide, I'm not sure how great this is showing up on everybody's computer, but if you can look at the slides, across the bottom, I have different abrasive sizes from an S70 all the way up to a 780. What the lines represent going across there are the velocities that the wheels are throwing the abrasive. And so, probably up to about 20 years ago, the industry standard for almost everybody out there, everybody was throwing around 245 feet per second abrasive. So that's going to be the red line with the red square. So we're through a simple formula, we're just, measuring that as impact in joules. So if you were throwing 390 shot at 250 feet per second, which is right at it, you are almost 0.5 joules of impact energy. Well, what has changed? One of the main things that's changed in the shot blast industry over the last 2 decades is the way that the wheels are bolted up and the way they go. We're not doing belt-driven wheels as often anymore. Yeah, there's still some times to where it is, but the most common out there now is direct drive, 3,600 RPM motors. Those are going to actually start to give you velocities all the way up to 360 feet per minute. Okay, so one of the things that so many customers and suppliers didn't really look at the best was, as you start to increase your velocity, you could actually drop down your abrasive size to get the same impact energy. That impact energy is what is actually doing the work on your part. It's doing the cleaning and everything on your part. So real quick, as we were talking about, that 390 slide gives you almost a half a joule of impact energy. If you were to jump up to 360 feet per second, which is incredibly, that's a lot of increase in velocity there, to achieve the same impact energy, you could actually drop 2 abrasive sizes. You could go down to a 280 abrasive size and you're achieving the same impact energy. Now, that impact energy, like I said, it has already been defined. That is the impact, and we'll talk about it in a few more slides. That's what it's taken to remove the scale, the sand, whatever it is on your part that you're trying to remove. Think about it this way. We have now dropped down 2 abrasive sizes. By dropping those 2 abrasive sizes, we're going to get more impacts per pound. Typically, that would equate to a faster cleaning time. Testing, all of that stuff should be done on that, but like I said, it should increase that. So another way, we'll kind of touch back on that one in a little bit, but another way to where some excessive abrasive consumption is occurring is the internal components of a wheel. They're actually grinding the abrasive. I want to show a slide real quick that is a high-speed photography. Hopefully everybody can see this. This is one we did a couple years ago. And what I really want you to lock in on is the impeller rotating around, and you'll see that wave of media. I'll try to use my cursor to show it. This wave of media right in here. So this is the impeller rotating around. You can see the arrows indicating the opening of the control cage right here. So that media in that gap right there is what is riding around there and then transferring over to your blades. You know, it's a violent action of what's going in there. That's just a sample of one of the videos that we had, and we'll touch on that in just a little bit again. Another area of when this abrasive consumption is occurring, abrasive impacting on itself. I've heard customers when I worked in the lab many times, you know, they'll make that statement: I've increased my shot flow, but it actually didn't decrease my cycle time. Instead, it actually increased my shot consumption. It's that give and take. Just because I want to throw more BBs against the part doesn't always mean that every single one of those BBs is transferring out onto that part to do any type of work. You actually, you know, I mean, you're flooding it. As the BBs are hitting it, they're bouncing. They're going somewhere. Some of them are actually bouncing back toward the wheel, and then the next wave of pellets are hitting on top of it. So you have abrasive impacting on abrasive. So that's going to consume the parts. It's actually not going to help you. You know, I'm throwing more BBs, but I'm not cleaning anything faster. That's why. Another thing of when the abrasive consumption is occurring is actually, you know, you're just missing the part. My abrasive is hitting the walls, the cabinet line, or something like that, and they're just not hitting the part. They're not aimed or targeted correctly. So here we go. Why is the excessive abrasive consumption occurring? All right, a couple things that we want to keep in mind as we've been talking about this. The higher abrasive speed, the velocity, it creates more kinetic energy. That goes back to the slide 2 slides ago when we looked at the how many joules it was between 250 and 360 feet per second. Another thing to keep in mind is you double the size of abrasive, you actually increase the impact value 7 times. And likewise, as you reduce it. So if you go from a 230 to a 460 shot, that impact value at a given velocity, just because of the size of that BB, increases that value 7 times. So as you're looking at doing modifications to an existing machine or something like that, it's just something that you want to take into account. Always throwing more velocity, it's not always bad, it's not always good. You have some other things that you can look at. You can look at different abrasive sizes going along in conjunction with the increase in velocity. As the velocity increases, the next point, the amount of abrasive thrown per minute decreases. And that's given that you're using the same horsepower in a wheel or the type machine. I'll be honest, 20 years ago, that one was one of the hardest for me to wrap my mind around. But it's true. So the slower that you're rotating that wheel, or you know, the tip velocity that the abrasive is coming off of, say a 14-inch diameter blade, a 16-inch diameter blade, or an 18-inch diameter blade, with the same horsepower, the same full load amps now can be thrown, you will always throw more abrasive with a smaller diameter wheel than you will a larger diameter wheel. So that increase in velocity, it gives you more impact energy, but actually you're not going to throw as many BBs. But you can start decreasing your abrasive size again, so you get those impacts per pound to kind of balance that out. It's just, like I said, it's a balancing act that really needs to be thought out. Lastly, one of the main fallacies, larger abrasive does not last longer. Actually, the larger the abrasive it is, the faster it's going to break down. Is it's hitting the part, it's hitting the walls, whatever it's hitting, it will actually start to fracture and break down at a higher rate than the smaller abrasive will. Again, going back to that impact value. Okay, so how can I reduce any of this impact energy consumption? When we were talking about the impact energy, I've kind of touched on it a little bit talking already. The first key, all right, we need to determine what abrasive size and velocity is correct for your application. You know, kind of from my pictorially what I've shown there, if you got too many big BBs, you know, we're just trying to break off that brown scale, sand residue, whatever it is. Our abrasive is so big right there and our velocity is so high, we're actually getting down and we're going to start to do some damage to the base metal. That's not good. And then on the slide right below that, if we have BBs that are too small, we actually may not be able to break down through the base, through whatever it is we're trying to get through in this, sand or scale. We're not going to remove it all. Our impact energy just isn't there. So how do we kind of, balance all of that out? Couple of things that we suggest, like I said, as I've talked about, some tips that you should look for when selecting the abrasive. Because I said that larger abrasive typically is going to break down faster. So you want to find the smallest abrasive size that is going to do the work that you need it to do. The reason you want to do that is because you're going to gain more impacts per pound. If you're throwing, I'm just tossing numbers out here. If you're throwing 460 shot, you might get 90,000 impacts per pound. But if you increase your velocity and you can drop down to a 330 shot, instead of 90,000 impacts per pound, you could gain 150,000 impacts per pound. Obviously, those impacts are what's doing the gross cleaning, and so it's going to clean it faster. Again, the larger abrasive doesn't last longer. There we go. You got to have it big enough to break the sand and scale. So you always want to try to choose the smallest possible size that does the job. Okay, so if you've been around this industry for a while, you've probably heard the term, and this is what you're trying to gain. You're trying to get a good operating mix. What is the operating mix? All right, it's a bell curve of different abrasive sizes. So you want to have that large particles that are going to do the gross cleaning. You have the small particles that are getting in there and doing the coverage. They're once the base layer is broken up, you can have some of the smaller particles in there getting in the nooks and crannies, the valleys. The medium particles, they do just a little bit of both. One of the things that I have always used as a rule of thumb, whatever abrasive size you're purchasing, if you're purchasing just a single size, a good operating mix is to have around up to three sizes mixed in below that purchase size. So if you're purchasing 390 shot, you want to have a percentage of 390 shot, and anybody can reach out to me afterwards. We kind of have some suggested percentages. But 390 shot, then you want to make sure you have some 330, some 280, and then some 230 shot. Obviously, once it gets down below that 230, you don't want to keep all the small stuff in there. You don't want to keep your 170, your 110, because that's getting really too effective for what we're trying to do, what you're trying to do with your cleaning. So you want to make sure that your system is pulling that stuff out, because if you don't, all it's doing is using up amps, power, things like that. So how can I reduce some of this? If the operating mix changes and you don't have proper additions, these are the things that'll occur. So what happens? What I'm trying to say here is very typical in our industry. What happens is an operator will put 390 in his machine and he's going to run it. He never really watches. He's never really, seeing what his operating mix is or anything like that. All he's doing is watching his amps on his wheel. And all of a sudden his amps are going to start to drop to where he's not full load amps. May take a week, maybe, 2 weeks, whatever it is. So what's he going to do? He's going to go get a 2,000 pound drum of shot, and he's going to go over there and he's going to slug his system. He's now going to throw that 2,000 pounds in there, and he's getting his amps back up. But a couple of things that happen when you do your system like that. You have your hotspot shifts. As your abrasive gets smaller and breaks down, the release point out of your control cage and off the blade tips, it actually does release slightly different. So your hotspot can shift. Obviously, the finish on your parts are going to change. If you're slugging your machine with 390 shots, say, and then all of a sudden you're letting it break down to 230 shot, the finishes are drastically different. So you're going to have an up and down of a profile on your parts. Your cycle times obviously will increase as that abrasive breaks down and gets to that non-effective size and everything. It's not doing the job that it's intended to, so it takes longer. And most importantly, as we talked about earlier with labor, you're losing control of the process. It's just kind of all over the place. Pictorially, one of the things that I've kind of thrown there, I just will toss out there an easy way to solve some of these solutions for an operating mix is right there with an abrasive adder. The way an abrasive adder works is it slowly meters in as it's needed through a abrasive valve and a level probe in your hopper. It will slowly meter in a certain amount of abrasive, so you're never slugging your system. I've had guys that are running these abrasive additives before tell me, they said, man, the problem is that thing doesn't stay open. My valve only stays open for 5 seconds and then it closes. So they want to go down there and switch the air line so it stays open the whole time. Well, that's the opposite of what you want it to do, because again, all you're doing is slugging your system. You want it to intermittently open and close to keep that good operating mix going. Okay, the next one. Why is some of the grinding abrasive consumption occurring? All right, from the video, like I said, we saw that abrasive is riding around, and you got to imagine that was a 3,600 RPM wheel. So that impeller was actually rotating at 3,600 RPM. A couple of ways that aren't thought about, but your abrasive consumption is occurring, is right there with the alignment of the impeller inside the control cage. I kind of highlighted the impeller was the part moving around, the control cage is stationary. If that thing is not aligned right, if it's loping or it's riding off to one side a little bit more, every time in that area, it's grinding abrasive. 3,600 RPM, it's grinding a lot of abrasive in that area. Another way is the abrasive is just not escaping the control cage. It's just sitting there and it's just riding around the loop over and over and over, and it's never transferring out of that control cage opening onto the blades and transferring to your part. That's never a good thing. You're just using energy and power that's not doing you anything. And then another area is the abrasive is violently transitioned from the control cage onto the blades. I didn't put it in here, but I have another high-speed video that kind of shows that transition of the abrasive coming out of the control cage. It is not, I will tell you, a nice fluid transition. Those blades are rotating around, and it is a very violent slapping action, almost like a paddle wheel. So those are some of the areas, again, where that abrasive consumption can be increased due to just what's happening inside your blast wheel. So here we go. How can we reduce any of this abrasive consumption? That's the million-dollar question. One of the things that you can do is machine the back face of the impeller. What that does is, these impellers are castings, typically. Most of them will have a parting line or something back there. And, in the old days, a lot of those impellers, when they seated inside that control cage and used your impeller bolt to bolt it in, they would lope. And, maintenance personnel, operators, whoever was changing it out, they would put shims in these things. They would pull them out, move it 20 degrees, try to put it back in there. And you just kept putting it in there to where it loped, but it didn't actually hit the control cage. If you couldn't hear it, that was good enough, and everybody went on. Well, nowadays you can do things like machining those back faces of the impeller. Everything is a lot more toleranced these days, so that you are assured on a machined impeller that thing is riding concentric inside the control cage at all times. You're going to have that same gap rotating around all 360 between the impeller and the control cage. Another area that you can do is make sure that you have the correct timing between the impeller vane and the blade. When we were talking about that violent transition of the abrasive coming out of that control cage onto the blades, all of that is actually controlled by the timing between the vane and the blade. Another good thing to look at is if you have a control cage, so that abrasive isn't getting in there and just riding the loop round and round and round. We want it to escape out. Having a control cage that has a recess in it, it actually forms a little bit of a funnel that always lines up with the control cage opening. So that abrasive, as it's riding around, kind of drops down into that funnel per se, and it's always going to be released onto your blades at that point. Another area to look at is closing the gap between the blades and the control cage OD. That gap where the blades come around. Too big of a gap, a lot of that abrasive will actually flow as it's coming out. It will go behind the blades because they're rotating around 3,600 RPM. You'll start getting wear on the backside of your blades and things like that. Trying to close that gap and minimize it is going to help that transition. So those, again, are some of the ways that you can reduce that abrasive consumption. Another way we talked about was the impact of abrasive upon itself. On this slide right here, it just shows, a couple of the options that are out there, depending on what you're trying to do. You can see here on the far left, there's a 2.5-inch wide blade. You know, by the time it hits your workpiece, it may be average 36, 40 inches away. Yeah, it spreads out a little bit, but you know, it's probably effectively, instead of 2.5, maybe 3.5 inches wide. Then you can have a 3.5-inch wide pattern. It's going to obviously clean certain type of machines a little bit faster, mesh belts, roll conveyors. But another option that should be looked at is the potential for a convex blade. A convex blade is actually going to widen that pattern out even more, up to about 30% wider. Testing has proved. If you have the right hump design and everything to kind of have that abrasive flow off, you can get up to about a 30% wider pattern. So earlier, when we talked about some of that abrasive consumption, you know, I've increased my horsepower, but I really hadn't reduced my cycle times or anything like that. All that's happened is my abrasive more. Again, look at something like a convex blade. It's spreading that abrasive out more. It's actually going to clean a little bit faster because now I can increase my horsepower and spread out the amount of abrasive that I'm throwing. Okay, another one. How do I reduce not hitting work? When we talked about earlier, you know, I'm aimed and it's just not hitting in the right area. I'm not hitting my part. I'm hitting my cabinet or the liners. A couple things that can be done there. On the left-hand side, the control cage. The control cage is what aims the abrasive. It's what's used to target it. It's the stationary part in the wheel, the relation of where that abrasive comes out of there and is first introduced on the blade. Most shop manufacturers will provide a number of different control cage openings. Here is a representative. I've got a 30, a 49, a 70, and a 100 degree. The smaller the degree opening, the less abrasive that comes out onto every blade, and it reduces and shrinks the abrasive pattern. It makes it a little bit shorter. So that's one area. You know, if you're just targeting on a certain type machine and you're just targeting a very precise area, maybe you want a 30 degree in that area. That way, it's going to aim it and funnel more abrasive into that tight little area. The next is with blade lengths. So here's some representative of a couple of blade lengths. You know, they go anywhere from 14-inch all the way up to about 26.5-inch. That relationship of how long that thing's going to ride on those blades is going to be able to give you a longer pattern. So there's, again, a couple of choices or numerous choices that can be made to try to help make sure that you're aiming your abrasive in the right areas. Down there at the bottom, another thing is you'll see a picture. It's indicative of what's called a concave blade. So it kind of funnels your pattern in. Obviously, it has to be the right application. You know, a rod, a bar machine, something like that. There's no need. It's only, you know, 1/2-inch diameter. Why do I want a 2.5 or 3.5-inch wide pattern when I'm only blasting a 1/2-inch wide part? So try to funnel that abrasive in so that it's not hitting my part. It's using abrasive, it's wearing components out, things like that. We try to minimize that best we can. Okay, so where are these consumable costs coming from? Some of them. The next one we were talking about was the abrasive waste. I kind of typed out a little formula there. What I'll say is anything above the natural consumption, as I talked about in one of the first slides, you're always going to have a certain amount of consumption of media when you're running one of these systems. We just want to minimize that. Anything above that natural consumption is waste. You know, this is just a simple way to track it. It makes pretty sense if you read it. You know, you want to record the wheel hour meter for at every abrasive addition, and then record how much you put in. So at 100 hours, you know, you put in 500 pounds. You mark kind of where you're at in your hopper at that time. You run it again. You have an idea of how much your natural abrasive consumption is. At the next 100 hours, you measure and see how much you got to put back in. If it's another 500 pounds, you're running about right. All of a sudden, if it's, you know, 700 pounds, you got 200 pounds that escape in that system to what we'll call waste at that time. Where is a lot of this waste occurring? Where is it coming out of? One of the main areas that it comes out of is from the separator. The separator's up on top of the machines typically. You know, there are lower level ones as well, but still it's more out of sight, out of mind. So if you get abrasive, I'm going to use my cursor again, A lot of times you'll get abrasive coming out of your trash hose on the end of your separator, or possibly even your fines hose with your dribble valve on it. I would say that if maintenance personnel or anybody ever comes in, you're looking over your system, that is definitely one of the first areas that you want to walk up to and check. You should walk over and check that trash tube and that fines tube. Find out if there's any good usable media in either one of those, because if there is, that's waste. It's a lot of money just being thrown out right there, and we want to figure out why that is occurring. So off your separator, why could some of it be occurring? All right, one of the things is a clogged screen right there on the left-hand side. Could be a clogged rotary screen. It could be the screen below your air wash separator. It gets clogged up. It's tramp metal, nuts, bolts, rags, whatever it may be that could get into your system. As they start piling up and clogging up that screen, your abrasive can't drain through. So what's it going to do? It's just going to pile up, and it's going to start transferring over into your fine side. And that's why you may see an insurgence of good abrasive coming out of your fines tube. So you want to make sure, again, part of your preventive maintenance daily checklist would be to go check your screens. Another area is maybe your rotary screen is rotating too fast. Actually, if that stuff's rotating around in there, that abrasive doesn't have time to drain through the screen. So it actually bounces all the way through and comes out of your trash hose again. Possibly your rotary screen may be rotating in the wrong direction. The way most of these separators are designed out there, the abrasive is supposed to ride on a certain side of the separator, and then gravity will take it down to your air wash curtain. If you're rotating the wrong way, you may not have the same angles on your separator, and therefore it's just pushing it out of the back of your separator. Another one, and this is one of the most common ones, is if you don't have a full abrasive curtain coming off of the air wash of your separator. What happens is you're drawing air across that separator. If you don't have that full curtain, air's lazy, it's taking the path of least resistance, and what you get what's called kind of like a curl. Is you're pulling all that abrasive across this open end, it's going to cause the last 2 inches, maybe 3 inches of your abrasive curtain that's cascading down right here, because it's a higher velocity here of air draw. It will actually peel this around and curve it around, and you'll pull good abrasive going back toward your dust collector and fines. That's a very common occurrence. I apologize on that. And then another area is a surge of abrasive and contaminants. We see this a lot in foundry applications and stuff like that. That first 30 seconds, maybe a minute that a casting is brought into the blasting chamber, obviously it has a tremendous amount of sand on it at that time. And so that surge of when you're blasting it and the bulk of that sand comes off in the first, minute or two, it's going to have an impact on how your settings of your separator and all are. So those are a couple areas, again, of why some of this waste from the separator is occurring. So the magic question again, well, what can I do to reduce any of these? As we talked about earlier, from your preventive maintenance, you can do a daily check of the screens. Another potential to reduce abrasive occurring from the separator not being a full curtain, it's called an abrasive curtain regulator. Basically, most manufacturers have something like this. It is a system that will make sure that your swinging baffle is closed until the abrasive is all the way across the lip, so that when it opens up, you always have a full curtain maintained. If you were to have a surge or something, it'll actually back off. It'll close down so that you're not drawing that air off of one end of your separator that abrasive is not at. One of the last things when we touched on, there are systems called a surge overflow. You can kind of see in the bottom right-hand side pictorially, having something like that into your system. That basically just goes into your screw trough, connecting your elevator head section to your separator. And it has an adjustable plate in it that drops down to about 50% loading on your screw that's feeding across there. So when you get that surge, before it ever makes it to the separator, it will actually funnel primarily sand, some shot, and it'll funnel it back down that tube to your lower reclaim, and then it slowly just meters it through the system as it's going around to feed it at a slower rate. Another area where some of the abrasive waste is occurring is from shaker scalping decks. You can kind of see right there on the right-hand side, scalping decks are going to have perforated holes that allow the media to drain through to funnel back into the elevator to go up. The next slide you'll see. So if they get clogged up, if those little scalping holes get clogged up with tramp metal, whatever it may be, again, obviously the media can't drain through there. So what's it going to do? I'll back up. It's just going to keep feeding down your shaker, and it's going to go to whatever refuse bin you have. So that's another area you always want to check, is that refuse bin. If you have a shaker reclaim, make sure there's not any good usable shot in it as well. Another area it's very visible, is obviously abrasive waste occurs from carry out on parts. A couple representations I've shown here. Obviously the one on the left-hand side, that's coming off a mesh belt. Visually, you can see that very easy. And you can imagine if I'm running parts like that on a regular basis, it's not going to take very long at all before all of a sudden I empty out the media from my machine because I've carried it out on parts. Another one that people don't always realize is the one on the right-hand side. If you're running, say, a ton blast system, if you have a real dense load that's kind of shown there, that abrasive takes a lot longer to drain through your dense load to make its way back to the reclaim system to funnel back up. How can you reduce them? Pretty common sense stuff. You can add a blow-off system. Is represented in those pictures. Those are going to help blow all that abrasive off before it ever off the parts before the parts ever come out. Sometimes if you have a system, certain parts will have pockets in them to where blowing the blow-offs, actually all it does is kind of move the abrasive around and they don't actually pull out of your system. So there are a bunch of systems you can put in that have a vacuum. You got to have an operator in there, but he may stick a wand in one of these holes or pockets to pull the abrasive out that way. On a tone blast machine, one of the things you'll have to look at is, increasing your post-tumble time. If you run a mix of parts, some of them are dense parts and some of them are bigger parts, that's something you want to look at. The bigger parts, the abrasive will excavate, drop down through your mill belt a whole lot faster. When you run a dense load, you may have to increase it 2, 3, 4 minutes so that you're not getting the abrasive coming out with your parts. Okay, consumables coming from just a consumable, the wear parts. Anybody who has run a shot blast machine definitely understands this one. The machines eat themselves up, and the parts that go with them eat themselves up. So how can we reduce any of that? Or let's start out, I apologize. When are some of these occurring? One of the main areas is off the blast wheel. If that blast wheel isn't targeted correctly, it's going to increase your wear parts. Pictorially right there, you kind of see I'm actually blasting off of my housing with a tremendous amount of my blast stream. So that's going to do two things. Obviously, it's going to increase my abrasive consumption. It's going to wear out my housing faster, and I'm not going to clean as fast. So those are a couple areas that you want to look at. When could it be occurring? Why are some of these occurring? Okay, so one of the common things is your blades. It's a very common question. When do I need to change my blades out? The rule of thumb on that is you want to change your blades out whenever they get to 50% through the thickness of your blade. That's time to change it out. They're not always going to wear nice, even, and smooth. Pictorially, you see right here on the top edge, I've got a wormhole or a little vein that came through there. That vein has gotten beyond 50% of the thickness. It's time to change those blades out. If you don't, as those blades start to wear out, one of the things that's going to happen is your blast pattern is going to shift. That relationship of when that abrasive rides on that blade and how long it rides as it's rotating around and released is a correlation of where it's aiming. So as you start to wear that blade out, it's going to shift that pattern. And then as it says there, it can also, as you're shifting that pattern, you're going to wear out your housing, cabinet, anything else because you're not aiming at your parts anymore. Another one, it's a control cage. Again, the same thing. The control cage, as it wears out, you can see pictorially here is that release point where it comes out of the control cage on my blades. As I start to back up and open that control cage opening more, now where it's captured onto the blades, where it's released and first hits the blade, has changed from the initial setup. So it's not going to ride around as long on the blades and release to the same point. Another rule of thumb, When the wall thickness reduces to about 50%, it's time to change the control cage out as well. Lastly, one of the wheel components, the impeller. Whenever you can read there, the impeller is worn when the wall appears to be forming a feather-like edge. You know, the purpose of the impeller is to sit there and keep that abrasive generated and fluffed, and it sets the timing coming out of that control cage onto the blade. As those veins start to get thinner and thinner, they're not generating and moving the abrasive around the same, and the timing is going to be off. So you can kind of see on the right-hand picture, all of a sudden I'm getting abrasive coming off on the back side of the blades. It can wear out some of your wheel components. It's going to be a more violent action inside the wheel. So that's, again, one of the main areas that you want to look at. Okay, so how can you be ensured that your wheel is targeted correctly? You know, the best thing out there is to do a hotspot sheet. You get a piece of 10 gauge steel or something like that, and you put it in as a representation of where your part would ride in that machine, and you run it. Depending on your abrasive size and everything, you know, you may want to run it for a minute, maybe 2 minutes. But it will actually, as you can see pictorially, down there in the bottom right-hand side, it will actually blue the plate. There's no, misthinking about where your pattern may be aimed at when you see that. You will know dead on where your pattern is. If you ever see it chopped off, they should always look nice and cylindrical like that, elliptical, excuse me. If you ever see it chopped off to where one end, the right end or the left end, all of a sudden is bull-nosed or flat off, that means you're probably bouncing off of an inliner or something else before it actually reaches your part. It's going to wear components out faster. Okay, another way that you can also ensure that your wheel is targeted correctly is a feature, something along the target lock system. Once you have done that hotspot check, you can actually lock down your control cage in place so that release point, that control cage opening, is in the same place. And when you do a simple tune-up change out, you pull your control cage out, you put the new one back in, it has to go into the same location. Most of these misadjustments on the targeting occur when maintenance personnel change a tune-up kit out. They'll put it in a wrong location, something like that. Testing has proved out that at 36 inches away from your part, for every 15 degrees on that control cage opening, that you move your pattern, or that you move that control cage by 15 degrees in the opening, it will shift your pattern 3 inches at 36 inches away. So you can imagine all of a sudden if you clock that control cage opening 30 degrees off, your pattern has moved 6 inches. That could have gross impact on your cleaning efficiencies or your wear consumable parts. Okay, another way that the excessive wear parts are occurring, is your separator functioning properly. Separator is probably the most second important part of a whole system. Blast wheels, in my opinion, being the first, the separator the second. The separator, along with the dust collector, it's like a huge vacuum. But as your contaminants and your blast media are cascading down, you have that full curtain across there. With your dust collector functioning properly, you're pulling through that curtain of media dropping down. What you want to do, you want to pull out all those contaminants, whether it's sand, scale, the non-usable media. You got to get that stuff out of your system. If you don't, obviously you're leaving sand in your system or scale. All that is going to do is accelerate the wear of your blast parts, your blast wheel components, and anything else that it comes into contact with. So having a properly run separator is key. Again, kind of going off of the last couple slides ago, if that curtain is disrupted in any way, that air is taking the path of least resistance. It's lazy, so it's going to draw through on an edge like that, and you're not cleaning your abrasive effectively. Another one that a lot of people they miss all the time, dribble valves. As that vacuum system is working and we're pulling from the dust collector off of the abrasive curtain, we want to be pulling what it was designed for. It's a certain CFM that was engineered, designed to pull across that abrasive curtain. This is a dribble valve that goes at the bottom of your fines tube. The one on the right-hand side, it's good. it has a little rubber flap and it closes off. You can see the one on the left-hand side is open. And this occurs in most places. The operators see that and they think it's supposed to be open, because if you don't, the media piles up, or the fines pile up right there. So they'll open it up and force it open. Problem is now when my dust collector is drawing air, I'm actually drawing ambient air from down here. So I'm not pulling all that air across that separator curtain. I'm pulling it up this tube. So I'm not as efficient at the separator curtain. These things are all designed so that with a certain amount of weight of the fines, they kind of burp. They'll slowly open up to release the trash and contaminants into a barrel like that. Another thing I'll key in on from a safety standpoint, always make sure that that is above the barrel. Never let it protrude down into the barrel, because it will fill up with shot then, could climb all the way up your blast hose and eventually, fall off, and there could be, 200, 300, 400 pounds there. Lastly, how can I ensure that the separator is pulling out those contaminants? Couple areas. We talked about the ACR earlier. Obviously, that one's going to come into play here, because if I'm using something like an ACR, I'm going to make sure that I have a full curtain across my separator the entire time. So that's going to be key. Another one are just the process controls. If you'll do a sieve analysis on your abrasive, that's going to tell you so much just by doing that. It's going to tell you, is your separator functioning properly? Is your dust collector functioning properly? Do some CFM checks. Check the airflow across the lip of that separator. Check it in some of the other key areas like that. All of those things are going to help run your machine a little more efficiently. I want to thank everybody for today. I know it was rather fast, but I was trying to condense a lot down into this time frame. So that really wraps up what I have right now.
Thank you so much, Jonathan. And to all of you who are with us, feel free to type in your question for John if you have any, or you can email him at that email address. We are running short on time, so we won't have a whole lot of time to go through the questions, but please know that if you do submit them, that there'll be some follow-up, and please take down his email address, and you can reach out maybe a little bit later. Jonathan, you had a lot of great tips and things to look at for reducing cost. But if we're just getting started trying to chip away at our cost, where's a good place to start, or what are some low-hanging fruit?
Yeah, probably some of the low-hanging fruit are going to be, again, making sure that your wheels are targeted correctly. That has a tremendous amount of impact. That one probably one of the most, because if your wheels aren't aimed at the part, it's going to increase your wear life, it's going to increase your cycle times and productivity, and it's going to increase your abrasive consumption. So making sure that those wheels are targeted correctly are probably the first key thing that you always want to ensure and lock on. It'll have the biggest impact. Secondly is always going to be the separator. Again, it's typically one of the most neglected parts of a system because it is a little more out of sight, out of mind. But having a properly functioning separator is going to reduce your running costs drastically. You're not throwing sand, you're not throwing scale, things like that.
Thank you.
Yes.
And we also had a question about whether the presentation will be available for reference. Yes, everyone who attended and registered will receive a link to the webinar, so you're able to review what you've already learned here today, pass it around to someone in your company who maybe is involved more directly with this. So yes, the answer to that question is yes.
And again, please, as Shannon said, anybody can email me at any time at that email address, and we can have a further discussion on any of this. Running through how to properly do a sieve analysis on your equipment and things like that.
All right, very good. Thank you all for joining us today, and thank you so much, Jonathan, for a very educational webinar. Have a great afternoon.
Thank you all very much. Bye-bye.